Between its use in digital cameras and on the web, JPEG is by far the most important image format in use today. The next version will be driven by AI. Here to tell us about that is Dr. Elena Alshina. Elena serves as the Audiovisual Lab Director for Huawei, as well as the Director of the Media Codec and Standardization Lab at Huawei. She's also co-chair and Exploration Experiment Coordinator for the Joint Video Experts Team Neural Network Video Compression Group, and Standardization Project Chair and Editor, along with Professor João Ascenso for the Joint Photographic Experts Group JPEG AI Initiative. Thanks for joining us today, Elena.
Thank you very much for inviting me. I'm very happy to share my knowledge and my experience in JPEG AI standard development.
Okay, why don't we just jump right into it? You've got a presentation all queued up. Why don't you cover the points that you want to cover?
Okay, that's the presentation about JPEG AI standard overview, design principle, and some number about performance of that. That's already introduction slides, which we do not need. But by the way, my major is the physics, and I got a PhD in computer science. And from my career, I was working both for the academia, I was teaching, and I was working for two big companies, Samsung and Huawei. Both are dealing with the smartphones a lot. And let's jump to the description of the JPEG AI. That's the project started in 2019 and with ambitious goal to encode images using only neural network-based technology, only learnable one, nothing classical. We plan to convert the image to the latent tensor representation here, encode that, and on decoder side extract the picture from these decoded images from this latent tensor representation. And this is almost done. Standards reached draft of the international standard, the IS stage, and it's currently on the ISO ballot. But this is not the only task which we typically doing with the images. Other applications are the super resolution, noise reduction, foreground, background extraction, image classification. Usually people decode the image, put it into another neural network, again create the latent tensor, feature tensor, and from this feature tensor use it for the solving the dedicated task. The general idea not to do that, but directly from the latent space representation, from the feature tensor, create a different decoder which will directly, without decoding the image, give you what you need. And from the call for proposal results which happened in 2022, we know that it is possible. We know, for example, for the image classification task, this way of dealing with the task without full image decoding, it's 10 times faster, 10 times less complex, and sometimes even more accurate. And that's the major focus for the version 2 of the JPEG AI. The version 1 will be focused only on the image reconstruction task. Why we decided to go with a JPEG AI decoder? In our testing set, there are multiple images, some of them already 8K resolution, and I would say as a user, it's the minimum resolution of the image which the smartphone customer would be interested in. And we encoded with a pretty moderate bitrate, 0.75 bit per pixel, with 4 different codecs: JPEG, JPEG 2000, HVC, VVC, which been the anchor for the JPEG AI, and this is the encoding runtime. You see that it grows exponentially. For the VVC intra encoding, we are spending 5 hours for encoding of this image. It's definitely not what customer would expect from the image coder. VVC is the perfect codec designed for the video, but most likely this is not what we can put into the product for the images. It's pretty well known why the all classical codecs spend so much time on the encoder. There is a search of the different variants of the encoding, but this search is already comparable with time we are using for the training neural network. So we just decided to train neural network, and I already can tell you that with a JPEG AI, with a GPU, here would be not CPU but GPU encoding, you will get the runtime just 9 seconds for the same image. And to start the training of the neural network, you need to decide about the loss function. Yes,
could I interrupt for a second?
Sure.
One of the things that was interesting to me with JPEG AI was the fact that it was designed to serve both for human beings and machines.
Mm-hmm.
So in addition to the quality aspect, could you talk about the functionality aspect?
For this slide. So should I start from the beginning or describe this slide again?
It's up to you. I just talk about the fact that it was designed to serve as a technology that could be used by machines as well as humans.
That's true. This is our original plan to do provide a coding engine of which takes the bit stream, conducts the entropy decoding, and produce the latent representation, feature tensor representation of the image. And this path will be shared for multiple tasks. And by training special dedicated neural network, it would be possible to do, for example, image classification or object classification or object recognition. All of those are possible because we know that in our current application, people decode it, put it into the different neural network and got the image. You can just design one neural network which directly drives you here. And by removing redundancy which are not relevant to this particular task, you can get, for example, object classifier task with just 10% of the ResNet 50, which was an anchor for this test, and less complex, faster, but even more accurate.
Okay, and we'll cover some of that as we get through the presentation as well. So thank you for that.
I hope. Okay. So that's where we can skip already. Then quality metric. To start training neural network, you need to choose the loss function. Since we decided to design the codec which would not search anything on encoder, we are losing the possibility to optimize encoder later on for the specific metric. We need to decide in advance what our quality metric would be. And that exhaustive study was conducted by the group of the experts before this JPEG AI project started. They collected images encoded with a classical codec, encoded with available by that time end-to-end AI codec, and collected massive database of the mean opinion scores from the 9 months of the different experiments in the lab and the viewing during JPEG meeting. And they just computed the correlation factor between the score the human gives to the image and the 14 different quality metrics. And they classify them to distinguish between the classically coded images and AI-based coded images. And what we see here, the longer bar, the better correlation is that, for example, for the PCNR-Y, for the classical coded algorithm, the correlation is something like 75%. It's not that high, but not that bad. But for AI coded images, it just dropped to 50%. It's basically PCNR tells you almost nothing here. And for the standardization, 7 the best correlated with the human perception quality metrics being selected and added to the common test condition.
And VMAF apparently made
and
it.
VMAF is amount of errors, which is a combination of different metrics itself.
Okay, good. Thank you.
Good. So, in the future, this database is available on JPEG site. We can test more metrics, of course. They probably will show better correlation, but through the standardization process, we been staying with well 7. So then I'm reporting you performance. This Bitrate would be relatively to the VVC intra, and it's computed as an average as BD rate in all those 7 metrics. So I would say it's not very fair comparison. We're using VTM software from the reference code from the JVET for the VVC. It's optimized for the PCNR, but that's what we see. We started at the beginning of 2023 after call for proposal response with a monster which has almost 1000 kilomag per pixel. Horizontal axis here is the kilomag per pixel. It's a million operation for one sample reconstruction with a 25% gain over VVC intra. And we immediately realized that it's not practical and created the simpler profile around 20 kilomag per pixel and with of course lower gain, and through the development process those dots are evaluated, and now we ended up with a 3 distinguished classes here, which is almost an order of magnitude in terms of the kilomag per pixel complexity. And we know that this green circle with 8 kilomag per pixel could be run on a device which not equipped with an NPU or CPU or GPU. You can just use CPU for this decoding. For the blue circle, this is the 16.7 time 16.7% BD rate gain over VVC intra. It's a 23 kilomag per pixel complexity. For this one, we have implementation of the smartphone. We have the decoder, which is decoded 4K image in less than 50 milliseconds. So,
okay, could you explain what an NPU is?
That demonstration is on a 2 years old smartphone of the Huawei, which is used a Snapdragon chip from the Qualcomm. I will have a slide with the details of that chip.
Can you just in general tell us what an NPU is?
That's exactly this one.
Okay.
Snapdragon 8 Plus generation first.
Okay, so some people may not be familiar with the term NPU.
Yeah.
So
it's a same thing as a GPU, but runs on a smartphone, which has like the small dedicated chip.
Okay, is it designed for AI type applications?
Exactly. It's collections of the operations which are typically used for the neural networks. Not all operations are available in the NPU. That's the one of the issue which we have to address, which is limits our fantasy. We try to design something which we can put into the product almost immediately. That's why we use the Qualcomm chip for demonstration, and we also have real implementation in Apple device provided by ByteDance, also very active participant of this standardization. So we are pretty sure that even 2 years old smartphone, or with a 2 years old smartphone, you would be able to use JPEG AI for the decoding.
Okay, could you go back to the slide that showed the 3 test cases?
That's fine.
So what conclusions can we draw about decoding capabilities vis-a-vis the GPU, the NPU, and the CPU?
So if you do not have any dedicated hardware, software for the decoding of the neural network, you will have to do it all on a CPU similar to the classical codec. Then you're recommended to use the simplest configuration. You will still have almost 12% BD rate gain. But if you at least have NPU, which is not as powerful as a GPU, and it's usually installed on mobile devices, then you can go with a middle profile and get 16.7% gain. And if you equip it with a good machine, if you're doing PC decoding, then you can go with the highest profile and get the highest gain, 24%. The best feature in JPEG AI design is that any bitstream which comes to you can be decoded by any of those decoder. And I will try to explain about that on the later slide.
Okay, thank you.
So that's we do anticipate something like free operation point. Profiles are not yet established. We call them super low operation point, base operation point, and high operation point. And here I show the graph in the kilomark per pixel, which you have already seen. And this is the decoding time on the GPU. This is the ratio to the VVC intra decoding, which of course happened on the CPU, but this is what we observe. In all of those cases, we have a number which is less than 1. So in a GPU decoding, you will spend the time decoding runtime less than that you spend with a VVC intro, for example. And that's just one illustration of the visual quality. This is the one image encoded with a pretty low rate, 0 to 25 bit per pixel, and so MSSIM, PCNRY, and VMAF number for this image. That's the VVC intra encoded, and I am switching to the JPEG AI encoded image, and you see like all numbers. I will switch back and forth, and you see all numbers getting better, and the visual quality is obviously getting better. Even it's in the red area, which is typically very hard to encode. Then one aspect which I have to elaborate on is the bits allocation. Very often I hear that in neural network you have very sophisticated bit allocation because you have attention mechanism, and the similar effect could be achieved by just enabling the QP adaptation inside of the picture in a classical codec. I asked one of my PhD students to collect the bits, spend it locally in the JPEG AI and VVC intra, which uses constant QP coding decoding. And the more white area here means more bits, more dark bits, less bits, and this is distortion. More red means the higher arrow, white samples means low arrow. We see that distortion more or less distributed equally, no too big difference between JPEG AI and VVC intro for this particular image, but the bits distribution in VVC intro is much more sophisticated because of the flexible block structure, which you can go to from the very large to the very small block size. I would say JPEG AI operates like as a constant block size 16 by 16. That's why it's absolutely not true that the visual quality improvement comes from the better bits allocation. And more information about decoder smartphone. We prepared this demonstration first for the 100 meeting of the JPEG, and the reason we prepared that, we would like to study whether it's implementable on a smartphone or not, which kind of operations are available for us on a GPU, on the NPU of the smartphone, and which are not, and so needs to be somehow restricted on the our standard. And we also been checking the runtime. Through this profiling, we figured out that very simple operation like the pixel shuffle, which do not have any multiplication and will not be appearing in a complexity if you measure only kilomark per pixel, multiplication per pixel, actually takes quite a lot of time when you put it into the smartphone NPU. So that's the configuration of this, our first demo. We took the software, middle operating point about 23 kilomark per pixel. We used the Huawei Mate 50 Pro smartphone, which is equipped with a Qualcomm Snapdragon 8 Plus Generation 1 chip. And we use SNP AI acceleration framework. That's the library which is publicly available. It's not the best way to communicate with the NPU. It might be even not the fastest way of the communication with the NPU, but it's this which anybody can check, and we did it for the purposes of the cross-check and the standardization. And I already mentioned it, why we've been doing that. We would like to check whether it's implementable on mobile platform, and also check device interoperability. We encoded images on the GPU of the PC, decoded them on an NPU of the smartphone, and we do not observe any issue. More, I have to take that special care was taken designing the standard to ensure device interoperability. Okay, first number was very, very bad, 70 milliseconds for the decoding of the 1K image. 1K image, 1000 by 1000. It's very small. It's not what customer will pay for. Already a few months later, both due to the code optimization and removing from the standard operations which are not friendly for the NPU, this time drop it to the 50 millisecond for the same size image. And the version we submitted for the DIS in international ballot, it's the 50 millisecond decoding for 4K image already. And have to emphasize this is not the fastest, it's the still proof of the concept, not the product level version. In a product, it definitely will be much faster. Then how it's happening? We take the image, we convert it to the latent tensor representation, which is smaller spatially, but has multiple channels. In particular, JPEG AI have 256 to 256 channels. And that's something happening here. It generates 2-bit stream. One is residual stream, which is the big one. Another is the Z stream, hyperstream, which contains information about prediction and entropy. And it's transferred to the decoder. You can notice that this middle part doesn't have any ID, but we have two possibilities for the encoder, 0 and 1, and 3 possibilities of the decoder. Because of the beauty of the design, any bit stream generated by any of those encoders can be decoded by any of those 3 decoders. That sounds like a cool feature for me. The neural network was to train it as just big octopus-like multi-leg neural network where all those 6 combinations been participating in the training. And what happened? What if you would like to add one more leg? It's certainly possible. Why I don't have this one? Okay, let's skip that. So on the decoder side, what's happening? You receive the stream, conduct entropy decoder, which is inside of this blue part. You get the latent representation of the image. This is the one with the multiple channels. And then you can choose decoder. There is a version of the decoder described in a specification, ID 0, which requires only 8 kilomag per pixel. You got the viewable image. If you spend more complexity on the decoder side, 23 kilomag per pixel, you get the better image. And the really longest one with a more than 200 kilomag per pixel operations with transformer, with very complicated attention mechanism. Here you have the maximum possible quality for this standard. It's of course hard. Yeah, please.
Excuse me for interrupting. How do you see this feature being used? When would I want to decode to minimal complexity as compared to maximum complexity?
So do you want to see how much the saving in the runtime?
Sure.
Okay, so if you decode it on the GPU of the PC, then here it's 1.5 times faster than the slowest one. The difference is not that high. This very simple, and the second complex more or less the same if you run them on a GPU. This one is 1.5 times slower. If you run it on the CPU, then comparison with VTM Intra becomes fair. Then this one as complex, the same decoding runtime as VTM Intra. This one is twice of the VVC Intra decoder, and this is 28 times more complex than VTM Intra if you look on the CPU runtime.
Okay, thank you.
Okay. And this picture shows you the difference to the original image after reconstruction, less red pixels actually indicates that the distortion is less. So more complexity results in a better quality, in the less distortion, even you don't really see it in this presentation due to this remote sharing. Then some more details about performance test results. As I mentioned, we measure bitrate in all those 7 metrics. Most of them are sensitive to the luminance, and VIF and VMAF slightly sensitive to the chrominance component. And you see that in the chrominance there is sometimes the drop. All results are reported relatively to the VTM intra, but from the study we conducted preliminary study of the correlation of the quality metrics with the human perception. Of course, luminance is much more important than chrominance for the human perception. Then you see that there is the configuration without the tool, since means 0 search on encoder, 12%, 16.7, 24, as I mentioned, with 3 hypothetical profiles. And if you enable tools, then you're getting 3% a higher performance. They also associated with some complexity. But what we need to look at here is the most important is encoding runtime. This most simple and the second the simplest profile, I would say, require fraction of the percent of the encoding runtime. Then on one of the slides I show 9-second encoding of the 8K image. That's the reality versus 5 hours encoding of this frame using VTM intra. That's, for me, is the biggest advantage of this learnable codec. Super fast encoding, and even it would be slightly worse visual quality than VTM intra or AVIF, and I would still buy that because of the speed. Many thanks to the software coordinator of the JPEG AI project who generated all those results for me. Another interesting feature which we not that easily can achieve in a classical codec, but are very naturally achievable with a learnable solution. We have the representation of the image in terms of this feature tensor. And it has multiple channels. 160 of those allocated for luminance, 96 allocated for chrominance. You can parse and decode them all, or if you decided that you do not have enough computational resources, you can decode just part of those. In this example, we took 16 channels from here and 0 channels from here, and it's 8% of the bit stream. It's a bad, but we can recognize what it is. For some semantics communication, that's probably already good enough. If you take 10% of the bit stream, just adding 1 channel from the major tensor, it already looks better. 24% of the bit stream already good, pretty good for the preview of the image, and this is 93% of the bit stream decoding example, which is look perfectly fine to me. And I don't know how you can achieve that with not changing the standard at all with classical codec. Here it's just the freedom of the decoder to decode all channels or just part of those. For the that was the quality scalability, and that's the feature which is useful for the partial decoding of that. Our bit stream, the big one, residual bit stream, is partitioned. You can take the whole bit stream, read it part by part, helpful for the pipelining, but if you decode everything, you got the full picture. But you can do a more smarter thing. You can decode only part of that, even extract only a smaller portion of this residual, and also take the smaller portion of that hat prediction and put it into the synthesis transform, and you got the part of the picture. It's quite useful for the scenarios where you have, for example, VR, a picture which is highest resolution, but you need to decode only part of it for the only viewport of that. So it's again a feature already supported by the standard, and we even have special mode where you allow it. If your PO encoder doesn't want to send the whole bit stream, you can just send this small portion of the residual which is only needed. Then what else is possible with the JPEG AI? Here I show sender side and the receiver side. We in some area here you have to follow specification strictly. Because the entropy parameter generated by neural network on the decoder side, you will require bit exact behavior here. Otherwise, symbols written from the bit stream are just wrongly interpreted. But beside of that, all other conformance points are weak conformance point. You can implement it slightly differently. Additionally to the free decoders we specified in the spec, one can go and train their own decoder using the training script by just adding one more leg to this octopus. You can train dedicated neural network which would not reconstruct image but directly will do image classification, or will solve the super resolution task, or will do the segmentation for you, or do some image enhancement, denoising, or SDR to HDR conversion. Like the scheme is pretty generic. Version 1, as I mentioned, it focuses on the just reconstruction, just image for the human, but we know that the machine vision task is also quite efficiently can be solved here, and that would be the focus of the version 2 of the JPEG AI standard. And of course, you can try to use this as an interframe for the video coding. Here I show an example of the VTM, VVC intra-coded first frame of the video, which is part of the common test condition of the JVET, and at the same rate, JPEG AI coded the same frame. See that runtime of the encoder is again 100,000 times smaller, and I will show how they really changing one to another. To you see that all texture which is lost here can be at least somehow preserved by JPEG AI at this very low rate. And this is another variant where we have high texture in this area, which is lost totally flat with the VVC. And if we change it to the JPEG AI, code it at the same rate, all this texture is preserved. So like, I'm not saying that the AI is the competitor of the classical codec, but there are some tasks which a classical codec cannot solve well enough, but AI can do. And that's the end of my presentation. Welcome to our Git, where all materials about the JPEG AI specification software is uploaded and available to the JPEG members.
Thank you very much for getting through that. A couple of questions. You talked about a little bit about applicability to video. How do you see that working? Is this going to manifest as a separate codec, or?
Yes, that's what is obvious thing to do. Intra-frame is encoded independently of the video. It doesn't matter whether you encode it with a classical codec or you encode it with a neural network codec. You can use GPU, NPU, you can use different device for the encoding of the intra-frame. And just put it into replace the intra-coded frame by end-to-end AI. We had that experiment few years back, maybe 3 years ago, reported into the JVET. We didn't continue this experimentation. We showed the great improvement of the visual quality. What is the obstacle on the way of implementing at least this very simple concept. Uh, we do not have the strong conformance on the JPEG AI. The part which is performed on a NPU synthesis transform is performed or described in a specification by float point operation. It means that every new device it might have different performance, slightly different, not drastically, but not bit exact. It's possible to quantize the neural network and achieve bit exact performance, but then you have to feed exactly quantized parameters of the neural network to the NPU. And unfortunately, at least through this Qualcomm library on which we use for the communication with the NPU, it's impossible. We do not have the control. We feed it with the float point parameters of the model, and it quantizes itself according to the how Qualcomm designed that. Similar thing, as far as I understand, happens on Apple NPU. Of course, High Silicon, which is a big friend of the Huawei, give us a bit more control over that, but that's the biggest obstacle of the going this way right now. Doing not intra-frame coding with end-to-end AI, of course, it's also possible. I have seen multiple papers. Some of them are written and published by my colleagues doing end-to-end AI coding for the video. Again, this is the proof that of the concept. It's much faster than the classical codec. Very similar ratio as we observe for the images. You don't have to do the search in this learnable solution. That's why for the ultra low delay application, which I allowed, including our teleconference, which requires almost immediate encoding of the video to share it to the partner, that's the very promising thing. For the It doesn't mean that classical codecs needs to be forgotten, and we still have this offline encoding scenario. We mostly watching the video from the YouTube and the Netflix, whom do not require low latency on encoder side or ultra low latency on encoder side. And I would think might be also the need for AI encoding in a video might be less. Okay, not necessarily it's a need for the AI video, but use cases for the video and for the images are slightly different. Then you receive the video to your smartphone, then you watch it on the screen of the smartphone. You do not enlarge it, you do not zoom it, you're mostly focusing on the action, on the motion. So that's 2K video, 4K video looks more or less the same on the screen of the smartphone. There is very unlikely that we will be watching 8K video on a smartphone. But if you receive the image, then you don't have any action, you don't change in the frames. You usually start to zoom and you usually start to figuring out where the details are preserved. And that's require at least 4K for any modern smartphone application for the pictures. Actually, camera of the smartphone are progressing much faster. What we get out of the camera of the smartphone, it's 8K or even higher resolution of the image. But when we send it through any messenger, then the first this messenger does is downsample the image and transfer it on the rate approximately 0.5 bit per pixel. We checked it for multiple messengers, and after receiving of the image, you can do this experiment by yourself very easily. All teeny details are lost. It means like the whole industry are suffering from the lacking of the good image codec, which handles with a high quality, really high resolution images. But for the video, At least for mobile decoding, we probably okay to stay with the 4K. And another corner use case where you watch it on a TV, which could be 8K, then it's entertainment scenarios, and you can encode it offline, and you're not limited on the encoding runtime. So I would see that the need for end-to-end AI coding for the fast or super fast encoding, for the application require fast or super fast encoding.
Okay.
Technically possible.
What's the timeline for JPEG AI simply for still images? When do you see that making into products that we're going to actually be using?
As I mentioned, the standard now it's under ISO ballot. The deadline for the ballot is October 10. And if ballots are positive, then it will be approved almost immediately by ISO and ITU as international standard. And implementation is ready. I don't anticipate that Huawei can put it into the product next day after it's approved. And we have some other companies actively participating in the JPEG AI, ByteDance, Danson, Hikvision. They all also have their own interest. For example, very fast encoding for the surveillance camera and of the Hikvision. Also, machine vision capability of the JPEG AI. They have interest to use that.
Okay, so how does that relate to, say, images on the web? When am I going to start using JPEG AI to compress an image that I upload to my website for general purpose decoding?
I'm not a person who is doing the cloud business. We do have one in Huawei. Let me talk to them. They also interested in having devices which able to decode that. It doesn't make sense to store it in a format and send it in a format nobody is able to understand. So we will first start with a smartphone implementation and see how it works.
Okay. Well, you talked about the fact that you could decode in a CPU, which should enable browser-based decode. Is that correct? Or
Yes, it's of course you can do that with a CPU.
Okay, this was very fascinating. I appreciate you taking the time today.
Thank you very much.